So in this video, I'm going to go over exploration 8.4c, just more practice with the harmonic analysis, coming up with the equations of these graphs. I'll go ahead and go back a slide and start at number 1 first. And so with this guy, I can see that the amplitude is staying constant and it's the sinusoidal axis that's changing. And so I know that I'm going to end up adding two sinusoids together. And so to start this one, I'm going to draw in the sinusoidal axis. And so right here I can see that this maximum goes up to 6, but then looking at this minimum point makes it hard to find this overall amplitude because this sinusoid is trying to go down to follow the sinusoidal axis. So if you were to take this piece and shift it up to where it normally would go to straighten this out, the overall height would actually be 1, 2, 3, 4, instead of this 4 in a piece. The overall height would be 4. So that tells me that the amplitude is 2. So I'm going to start my sinusoidal axis 2 down from this maximum. So then right here, here's an inflection point. I know that we're going to end up crossing right through that guy. And again, you can see it's 2 above, 2 below. Up here, same thing. Here's another inflection point. 2 above, 2 below. Same thing here, here, and here as well. So this would probably be enough to sketch our graph. So it's going to look something like that. And so for this larger equation, I can see that it's a cosine since it's starting at its maximum point, and the amplitude is 1, 2, 3, 4. So the purple equation, 4 cosine. Now looking at the period of this cosine, it's 90 degrees. So we put that over 2 pi, over 360 to find the dilation factor. So this would be 1/4. So in the equation, I have 4 theta. So now I need to write the equation for this smaller sinusoid. And so I can see that it is a sine function because it's starting at the sinusoidal axis. It's starting at an inflection point. And so I am going to use sine, and the amplitude is 2. And keep in mind I'm adding these. Okay. From here we need to find out the adjuster, okay, what the dilation factor is, and inside here will be the reciprocal of that. And so we have to work with what our graph has given us. And so I can see that I have 1, 2, 3, 4, 5, 6, 7, 8 cycles in 90 degrees. And 90 degrees. Well, that means then if I were to extend this out to 360, that I would need to multiply this by 4, which would mean I'd have 4 times the amount of cycles, so we'd have 32 cycles in 360 degrees. So that means that I'm making one cycle 32 times smaller than normal, so we write in 32 theta. Okay, so we're done with the first one, so now let's take a peek at the second one, where we can see that the amplitude is changing the entire time. And so again, to start off, let's draw in the larger sinusoid. And so it's going to look something like this. And I'm only going to draw in 1 cycle. You could obviously draw in more if you wanted to. So this larger function is going to be a cosine, starting at a maximum, and it starts 5 up. So my amplitude is 5. It finishes after 120 degrees. Normally the period is 360, which means it is 1/3 of the normal size, so I put in 3 into the equation. So I have 5 cosine of 3 theta. I'm going to multiply this, and now we need to find the equation of the smaller one. So I can see that this equation is also going to be a cosine since it's starting at a maximum point. I don't need to worry about a number in front of this cosine because the amplitude is the other cosine function. The harder part here is finding how many cycles there are in between 0 and 360, especially because we don't even have this graphed all the way to 360. So I'm going to count my cycles in between 0 and 120. Now this one is a little different than the others that we've done in class, because right here is my first tangent point, but nothing has happened yet. And so I'm not going to count that as one cycle because I don't even have a start of a cycle yet. This is literally nothing at this point. And so I'm not going to count this as one, but this does show me one cycle. So then the next point would be at this one right here. And so keeping this width the same, this would be my next tangent point, where here would be another, here would be another. Again, it's hard when you get down close into the x-axis to figure out where that point actually is, but just keep in mind the distance, one size of a period. So this would be the next one, this would be the next one, and then this would finish it out. So in this one, I'm not going to count the points, but they do help me see the start and the end of cycles. So since nothing happened here, this would be one cycle, 2, 3, 4, 5, 6. I have 7 cycles in between 0 and 120. Well, to get to 360 then, I know that that would be 3 times larger than 120, so I'd have 3 times the number of cycles, which would end up being 21. So the cosine is 21 times smaller than it normally is. And again, this one was different because my first tangent point started at the y-axis, and so I didn't count this one like the others, 1, 2, 3, 4, 5, 6, 7, 8, because nothing happened here, and we had 7 full cycles in between. So now we're going to look at number 3 and 4, and so keep in mind that we are in radians. This first one, the amplitude is changing. That tells me that we are going to multiply 2 trig functions together. Here the sinusoidal axis is changing, so we're going to add 2 trig functions together. Okay, just like the others, I'm going to draw in the larger sinusoid first. You could draw in a lot more than one cycle, but I'm just going to go ahead and stop after one. The larger one we can see is a cosine function again. The amplitude ends up being 3. And 1 full cycle takes 2 pi, which means we haven't adjusted that at all. So that'll just be 3 cosine of x. And we are multiplying that by whatever this guy is. So on the inside, we can see that we're starting at the origin, so I know this is going to be a sine function. And so now I need to count how many cycles there are in between 0 and 2 pi. So here is a piece of 1, so I'm going to count 1 there because this piece right here will match up with this left over to make 1 full cycle. So I am going to count this as 1, 2, 3. Down here again it gets tricky figuring out where to place that point, but once you look at that spacing, it does help you figure out where those need to go. And so continuing that spacing, there'd be one right here and right here. So we're at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 cycles in between 0 and 2 pi. That means in order to fit 15 cycles, we made it 15 times smaller. And so we finished that out with a 15x. So then on the last one, number 4, we'll go ahead and try and find the center. So you can see that we're going to start at the origin here. And so it looks like it's going 1, 2, 3, 4, a little bit more than 4 above, so it's safe to say that that amplitude is going to be 4 if we leveled that out. So we could graph a couple other points. This would be right in the center here. You could go 4 below this maximum. Looks like is maybe right here. Ends up being the maximum. It's hard to see on mine. So you can go 4 below either of these points. 1, 2, 3, 4. So maybe that would be a point right there. Here would be another inflection point. Halfway between, again, I'm going to go 1, 2, 3, 4. So our larger sinusoid is going to be this sine function. So we can see that it's sine, and the amplitude is going to be 2. So I'm going to start with 2 sine, and it finishes 1 full cycle in 12 radians. And so I can't actually, so the period is 12, and so we're going to have to do a little work to figure out what goes into the equation. The period is 12. The period's normally 2 pi, so we will have 12 over 2 pi. You could simplify this to 6 over pi, which means in the equation we put in the reciprocal of the dilation factor, so pi over 6x. So then the next one, the smaller sinusoid, we already looked, again the amplitude looks to be a little bit more than 4, but that's just because it's on the way up. So the amplitude is 4, and we are adding. It's another sine function since it's starting at the origin. And so now we have to figure out how many cycles there are. And again, you have to use what you have on your graph. And so I don't have 2 pi on my graph, so we're going to have to work with this 12 radians. So I'm going to count how many cycles are in between 0 and 12, and that's 1, 2, 3. And then here's a 4th, 5th, 6th, 7, 8, 9, 10, and 11. So we have 11 full cycles in 12 radians. Now, to find how much smaller we made these, to find that dilation factor, we need to figure out how many cycles there are in 2 pi. And so from here, I can cross multiply, and I'll get 22 pi is equal to 12x. Divide both sides by 12, and x will equal 22 pi over 12. We could reduce that down to 11 pi over 6. And remember, what we were searching for is how many cycles there are in 2 pi. This is how much smaller we made it. And so we can put in the 11 pi over 6x. Okay, so again, you're probably thinking, hey, we should be putting in the reciprocal of this. But what we were doing earlier is if we had 15 cycles, that means that we made it 15 times smaller, which is 1/15. So we plugged in 15. Down here, we had 11 cycles in 12 radians, so we need to know how many cycles fit in 2 pi. So we could fit 11 pi over 6 cycles in 2 pi, which means that we made it 6 over 11 pi times smaller. So this is already the reciprocal, since that's how many cycles would fit in 2 pi. And so this is our final equation.